Because it's been lottery, but like even if it's not gonna be on the final, I just wanna know how it works. I'm not knowing how it works.
Yeah, if you can explain that to me later on, that'd be great.
I'm sorry, but I think after dinner we may need to work on something now.
Yeah, I think it has something to do
20
with it.
minutes, and I'll finish this. And
Yeah, something.
Alright, so today we're going to be discussing the midterm solutions. And yeah, is there anything that you guys want me to go through before we start? Anything that you were particularly curious about? Other than SQL.
What was on the midterm you got? Other than perceptron and like definition stuff?
Linear classifier, linear regression, classification, Bayes rule, perceptron, regularization, and then decision tree and concept lighting.
Oh, I remember one question says like whether a single perceptron algorithm will always produce the same output no matter like in what order the inputs are all right. So
Yeah.
what's the answer to that one?
What's the answer to that? Okay, yeah, we can do that one first. Is there anything else that you guys are curious about? So that was question 7.
The optional one, the last one, I guess.
Sure. And then is there anything else?
Just a quick clarification. So for the perceptron algorithm, the updates only happen when there's a misclassification.
Yes, that's
Okay.
right. Is there anything else that you guys want to go through first? Okay, let's do it. So question 7. Oh, that's right. That's not question 7. The one that you're asking about is question 5. Okay, so problem 5, we're given a perceptron that is fixed. So this is just an inference. The weights are fixed, and we have some data set S, and then we do a permutation on S to get S prime. So now our question is the number of errors for the perceptron on S, we'll just call it perceptron like W, is this equal to the number of errors for S prime? Does anyone have an idea about that? So the answer is that the numbers of errors is the same, yes. And the reason for that is because W is not updating, right? So W is fixed. It doesn't matter what order it sees. There's no state that's carried over from one like classification to the next. So the thing is acting exactly the same independently of the order that it sees. So if this was during training, then the answer would be no, because then one update would affect the next, and the number of errors would depend on the order that you go into. But in this case, we have that there is this exact same amount of errors. I'm saying something else. I'm actually recording this one for another student.
Huh?
I'm recording the lecture for another student.
Oh, sorry.
Yeah, sorry about that. Let me just, okay. Cool. So the answer is yes. I think that's it actually. Oh wait, no, okay, so yeah, then the answer is, the question is why, it's because W is fixed, so they're all independent. Okay, then the last question, 10. So we're given 4 lines, right? So we have, let's say, 1 here, 1 here, 1 here. So these are our points, and we're given 4 lines. So line 1, say this is line 2, and then let's say that this is line 3, and then let's take one more line. Okay. So we have A, B, C, and then D, and then we have 4 corresponding loss functions. So L1 is MSC plus lambda. Okay, right, so then we have theta and theta naught. So theta equals the slope here, and then theta naught is the bias. So we have MSC plus lambda, and then a regularization on theta. And for the second one, we have the same thing, but lambda is now 10 instead of 1. So here, lambda is 1, and here theta naught and theta, and lambda equals 1. And then for the fourth loss, we have the same thing, and lambda equals 10, and a penalization of both. So the question is, we want to match each of these losses with the corresponding line. And does anybody have an idea about how to do this one?
Basically, I think for the slope, the more you penalize it, the flatter it gets, right?
Yes, that's right.
So for both lambda equals to 10, it would be A and D for like both of them will be flatter.
Right, so we know that 2 and 4 should correspond to A and D. So now which one corresponds exactly with which one?
Since you penalize the bias, so that I think it would be closer, like it would be lower for L4. So L4 is supposed to be D, right?
Yeah, that's right. L4 is D, which means that L2 is A. That leaves us 2 more, B and C. So what do you think about that one?
And similar idea applies to L3, which would be lower than L1. So for
So L3 is B or C?
so B should be L3
Why is B?
because
L3?
B is flat. Wait, no.
So C is L3, right? Because
Right.
it's lower, so it penalizes the bias. So these two, yeah, these two should have the same slope. So sorry, that's my bad. Yeah, they should look like that. And then this one is L1. So L2 is A, L1 is B, L3 is C, and then L4 is D. That's the answer to this one. Does that make sense to everybody? It's okay if it doesn't make sense, I can go over it again. Okay, let's move on. So that's 5 and 10. All right, let's go to question 1 now. So question 1. So we have some points like this. Is this linearly classifiable? No, obviously. Cool, moving on. Not linearly classifiable. How do we make it linearly classifiable?
Transformation.
And what does our transformation look like? Yes, you can just describe the intuition, and then I'll write the math.
X squared, Y squared, XY.
So the intuition is that we want to use the radius, right? We want to use the radius from the circle in order to determine whether or not it's linearly separable. So in some sense, you could transform this into polar coordinates, right? And then you would get something like this. And that's obviously linear. That's obviously linearly separable. It's very easy, right? So the question is just, okay, well, how do we construct this feature to do that? So the answer, oh, sorry, I should specify the middle here is C1, C2, and the radius here is R. So the way that we do this is first we want to transform everything to be at the origin. So we're going to subtract each point from C1 and C2. So my transformation on X should look like this. X1 minus C1, X2 minus C2. Okay, so now I've transformed everything to the origin, right? And then my next step is I'm just going to square each of these because that gives me the radius, and then subtract that from r squared. So now note that if this value is greater than r squared, then that means that this thing is outside of this circle. And if this value is smaller than r squared, that means that it's inside the circle. And so this is the transformation that you want to have in order to make it linearly separable. Does that make sense to everybody? Yeah, go ahead.
You shouldn't have to subtract r squared out, right? It would still be linearly separable otherwise. It would just be like shifted.
Well, if you didn't subtract by r squared, then this would be strictly positive, right? So then by perceptron, everything would be positive in that classification, so it would be incorrect. So you do have to subtract by r squared here. Yeah. Since you want the 0 to be your decision boundary, right? Okay. So the second question. Okay. So we have a linear regression. What kind of loss do we use for this kind of problem? Anyone have an idea?
Can you repeat the question?
What is the loss that we use for linear regression?
Mean square.
Yeah, that's right. So we use MSE, which is 1 over n sum I. Okay, then the next one. Okay, so if we had another loss, if we define a new loss, 1 over y minus y hat, is this a good or a bad loss function in y? Bad loss function. Why do you think it's bad?
The higher the distance, the lower the loss function.
Yeah, that's right. So if we plotted this, where this is y minus y hat, or distance, and then this is L, then you would get this, and you'd also get this. So there's two reasons why this is bad. You mentioned the first one, which is that here, as the distance gets closer, we actually increase the error, which makes no sense. And the other is that we have a discontinuity at 0. And so if you had y hat, or I guess if you had y hat to be slightly smaller than y, then you would get almost negative infinity loss, which is really good. Like that's what you want. But then if you just make that slightly larger, then you get almost positive infinity loss. So for those two reasons, it's a bad loss function. One is that there's a discontinuity, so it's not differentiable at 0. And the second is that it actually is convex or concave, so it's going to be decreasing as the distance goes up. All right. Next question. So, all right, we have dogs and cats. This is the classic questions. We have dogs and cats. So we have 300 dogs, and 150 of them are classified correctly, and 150 of them are classified incorrectly. And then we have 700 cats. 100 are classified as dogs, and then 600 are classified as cats. But we're going to take dog to be the positive class here. And now the question is, can someone give me the contingency table? Any brave souls out there? So, yeah, go for it.
I don't remember the whole question.
Just, yeah.
So let's say predicted and actual,
Okay.
dogs, cats, dogs, cats. 150. These are dogs, right?
Yeah, those are dogs.
value?
100, sorry.
100, right?
Yeah.
And then 600, right?
Yeah, perfect. And then you can draw the totals too.
Okay.
You can erase that. You can see. Okay.
Okay.
Awesome. Yeah, very well done. That's perfect. So, this is great. And the next question is, what is the false positive rate for this table? You don't have an idea.
It should be the number of false positives over the number of negatives. So that'd be like, I think that's 150 over 750.
Okay, so we think it's false positives over false positives plus, this is gonna be true negatives. So we have 150 over 750. That's not quite correct. Or maybe I'm not, actually, I think I'm incorrect, sorry. This should be 100 at the top, right?
Yeah, unless I can't read the.
Yeah, no, you're right. So this should be 100 at the top. Because this is a false positive, right? So this is false positive.
Are dogs positive or?
Dogs are positive. So this is predicting this dog. Right, so this is going to be a false positive.
Okay.
Wait.
I thought it was cats that are being predicted as dogs.
So we have the actual on this side, and then the
Oh,
predicted.
it's, okay.
Yeah, yeah,
I flipped it and added to that.
yeah, for sure. So this is false positives, and this is false negatives, right? And then this is true negatives, and then this is true positives. We have false positive over false positive plus true negative, or 100 over 100 plus 600, which is 1 over 7. Yeah, that's right. Good stuff. Okay, and then the next question. What is the false negative rate?
Over 800?
Yep, that's exactly right. So we have 1/2, which is the same thing as the number of false negatives over the false negatives plus true positives. All right. So for the false positive rates, we always sum this like horizontal side, and then for if you flip the table, there would be summing on the columns. Okay, and then for C, what is the error rate and the accuracy? So what is the error rate?
It's the false positives plus false negatives over total positives and negatives, the entire totality of the data set.
Exactly, and that is going to
It's
be,
just 100 plus 150, so 350 over 1,000.
yeah, so 250 over 1,000, right?
Or, yeah.
Right, so 1/4. Exactly, and then what's the accuracy here? That's just 1 minus the error rate, or 3/4. All right. And then finally, what is the precision? Yep, that's exactly right. So our precision is going to be the true positives over the true positives plus, I believe it's false positives, right? Yeah, false positives, which is in our case 3/5. Alright, well done guys. Next question, Bayes rule. So in this question, we have two binary variables, the color of the box and the fruits. So we have blue boxes and red boxes, so box color, and then we have fruits. So we have the orange, and I think it's apple, right? Yeah. Alright, and we're gonna use Bayes rule here. So we have that the probability of the box being red is 4/5. Wait, sorry. 2/5. And then it being blue is 3/5. Apple and orange, so that's not given to us directly. We'll find that in a second. So the first question is, if we know that when we have the box being blue, that we get 9 times for apple. So when the box is blue, we get 9 apples and 3 oranges. Then if we were to sample a new fruit, what's the probability of it being an apple? It's just 9/12, right? So it's just 3/4 here. Because we sampled 9 apples before and then 3 oranges before, so we know that it should be 9/12. This is just empirical probability. And then the next one, so what about the probability of an orange given that it's a blue box? Yep, just 1/4. So this is P of apple given blue box, and this is probability of orange given blue box. Okay, next question. The next question is, oh wait, sorry, this was if it was, okay, yeah, okay, whatever. And the next one is red, so in the actual term, these two are switched, so this one is A and this one is B, but it doesn't matter for our sake. Oh, I should specify, O stands for orange, and then A stands for apple, B stands for blue, and then R stands for red. Okay, so A given R. A, we get a 2 for here, and a 6 for here. So what is the probability that it's going to be an apple given that the box is red? What is it?
4/8.
Yep, exactly. So 2/8, or 1/4. And here it's just going to be 3/4. Okay, next question. What is the marginal probability of selecting an apple? So marginal means that I just want the total probability.
So that would be the probability of selecting an apple, times the probability of selecting an apple from the blue box, plus the probability of selecting, probability of selecting the blue box, followed by, or multiplied by, it'd be easier if I read it. I can't, if I try to do this in my head, it's not gonna,
I got you.
work.
Probability of blue box
Yes.
times probability of apple given blue box.
Perfect, and probability of red box times probability of apple given red box.
Exactly. Very nice. That's exactly right. And this is going to be, it turns out that this one is, okay, yeah, you do the calculations, you get what I'm talking with. I know all of you guys in here know how to do arithmetic, so we're gonna move on. And then D is, let's see, okay. So now we want to use Bayes' theorem. We want to know what the posterior distribution of selecting the box being blue given that my fruit was an apple. So in other words, we're going to go backwards now. So what's the probability of my box being blue given that I took a apple as the fruit?
I think this is where you use Bayes' theorem, and you can rewrite it as, I'm gonna write it down and say it because
probability of apple given blue times probability of blue. Over probability of apple.
That's exactly right. Is that what you're gonna say too?
Yeah.
Okay, great. Alright, how much time do we have? We're gonna go on a quick tangent. Who here has an intuitive understanding of Bayes' rule? Raise your hand if you have an intuitive understanding of Bayes' rule.
I know how to apply.
No one has an intuitive understanding of Bayes' rule yet. That's sad. Okay. Alright, well now after this, you guys are all gonna have an intuitive understanding of Bayes' rule. Because Bayes' rule is extremely important, so it's worth it to do this. Also, you can just watch 3 Blue 1 Brown's video on this. He does a great job. So you can just do that, and it's that will also give you a good understanding. So what is Bayes' rule? The easiest way to remember Bayes' rule is by starting from a joint probability with P of x and y. And we know that we can rewrite this into P of x times P of y given x. But we could also do it as P of y given P of x given y, right? So we know all 3 of these things are equal. And Bayes' rule is just this one, right, equals this one, and I just divide both sides by P of y, right? So if I just divide this by P of y and this by P of y, then I get Bayes' rule. And I could do it the other way around. I could divide both sides by P of x. And this way I find it's really easy to remember Bayes' rule because this is symmetrical. So you just start from the symmetrical way and then you just divide out. And then intuitively what we're doing here, right, when we say P, what is P of x given y, right? So what this intuitively means, right, is if I started from this being my entire universe of all the possibilities, and let's say like this was the probability of A. So basically I'm gonna throw a point uniformly across this universe, and if it enters this thing, then that means that my event was sampled, A was sampled. Okay, so the probability of A happening is the area of this thing divided by this whole area. So intuitively, the area of this thing is like how large the probability is. So if I had an event, right, so let's say this is x, and then this is y, so this is x, and then this is y. The probability of x and y is going to be what?
Probability of x plus probability of y minus the intersection.
No, that's probably x or y.
Oh, and y.
Yeah. X and y, that's just this part, right? Just the intersection. Right. So when we say what is the probability of x given y, what that means is effectively that we're just shrinking this universe down to y. Because we know that y already happened, right? We are conditioning on the fact that we already know y. So what that means is that instead of considering from omega, we just consider within this universe, this constraint, because we know y happened. So what's P of x given y here? Well, that's really intuitive, right? It's just P of x and y over P of y. And you'll notice that is exactly Bayes' rule. That's where Bayes' rule comes from. So what we have here, right, is that the P of x given y equals P of x and y over P of y. And we can just rewrite P of x and y as P of x times P of y given x. And that's where Bayes' rule comes from. Now this is really cool, right? Because in this example I showed you, this is very simple. X and y are kind of like these dependent events that are happening at the same time. But why Bayes' rule is so powerful is because it allows us to reverse the direction of time. It allows us to go anti-causal. So if we assume that there's some causality here, like x causes y, right? Then I can actually get x just by observing y. So if I know what the probability of y given x is, so if x causes y, right? Then I can go backwards. I can get P of x given y from that. So this allows me to do inference, and that's why Bayes' rule is so useful. So even though in this example it's very simple, Bayes' rule is actually very powerful because it allows us to reverse the direction of causality. It allows us to reverse the direction of time. So an example in this case, right, is here we're sampling the box first, and then from the box we sample a fruit. But what we want to do in this one is actually go backwards. Say we already sampled the fruit, and now we want to know which box we sampled from, right? So we can go backwards in time, which is really cool. Okay. Does everybody understand base rule better now? Great. I'm happy. So, let's see. Right. So let's try this one last time. What is the probability of the box being red, given that my fruit is, let's say, an orange? So we're going to constrain the universe to the fact that it's already been orange. And now we want what? We want the universe where both of these events happen, the orange and the red box. And we know what this is because we already have P of R and P of O given R. So P of R here is going to be 2/5, and P of O given R is going to be 3/4. And so now you can just 2/5 times 3/4 goes here, and then over here this should be this sum here, so it'd be 2/5 times 3/4 plus 3/5 times 1/4, and that gives you some value. All right, let's move on. So question 6. Question 6, so we have a loss function. We have MSE, so J equals 1 over M. And then we're going to add a regularization on the weights. And we're going to set lambda equal to 0.2 here. And now the question is, we just want to calculate what the loss is. And we're given like some y values, so let's say like we had, I'm not going to actually do the calculations up, but let's just say we had like 1, 1, 1, -1, -1, and we did 1.2, 1.5, 0.3, and then maybe like -1.5, 1.2, -2. And let's say that our weights was like 0, 1, 0. So then we need to calculate this loss, right? How would we calculate the loss for this case?
Well, J is the loss function, right?
That's right.
So we can plug in the values for the summation for yi and y for that portion.
Yeah, that's exactly right. So, sorry, this should be y hat. So y hat means it's coming from the model. It's like model output. So yeah, so we just take these two numbers, subtract them, so we get 0.2, square it, 0.04, and then 1, 1.5, 0.5, 0.25. You can do that for everybody, sum it all together, take the average, and then just add that to this guy's L2 norm, which would be 0 squared plus 1 squared plus 0 squared square root, which in this case is just 1. And then take 1 multiplied by lambda, so that's 0.2. So 0.2 plus the summation of the squares here, average. Does that make sense to everybody? Okay. All right, so the next question, we're going to do some perceptron updates. All right. so here's our data. We have 2, 2, negative 2, negative 3, 2, 1, 1, 4, and then our labels are positive 1, negative 1, positive 1, negative 1. We're going to initialize the weights to be at 0 and assume that there's no bias. So there's no bias. And now we want to find what the weights are going to be. So when W transpose X is greater than 0, then we call this positive. And when W transpose X is less than or equal to 0, then we call this negative. So now the question becomes, how do we update this thing? Can anybody tell me what an update rule is?
It's W prime equals W plus, I believe it's the learning rate N. It's not an N exactly, it looks like I guess it could be alpha too.
Oh, yeah, you're talking about eta.
Yeah. And then we have YI and XI.
Very well done. Get a star. Yeah, that's exactly right. And you know where this comes from, your bonus points.
Your professor went over it in class, but I don't recall.
This is the partial derivative of the loss with respect to W. So that's where this comes from. And that's why this magic works, because this is going to take our loss and make it smaller. I should specify it's a negative. Okay. If W is a vector, then this is the gradient. Okay, so let's do the update. So we start from 2, 2. So what is the dot product between W and 2 here? So we get 2 times 0 is 0, plus 2 times 0 is 0. And so we're going to classify that as negative, which is incorrect, right? And so now we're going to update the thing. So what should the new W be after the first update? I missed the negative here, by the way. It doesn't change anything though. Can anyone tell me what the new W will be?
What's the learning rate?
Oh, sorry. Alpha equals, or eta equals 1.
So YI should be plus 1, right?
Yes.
Then it would be minus 2 plus, so basically minus 2 and 2?
Exactly. So our new W is going to be negative 2, 2. And now, let's say we were going to do that classification again. Negative 2 times negative 2 is what? It's 4, plus 2 times 2 is 4, so we get 8, right? 8 is very positive, and now it's correct. Wow, magic. Right. The reason why that worked is because it's this. So that's the beauty of partial derivatives, they're very powerful. So the reason why that just became the correct classification is because this is literally how we decrease the loss. And then if you want a geometric interpretation too, then this is what's going on. So if I had a W vector like this, right, then remember that the decision boundary is always orthogonal to the W vector. This is because on the decision boundary, that dotted with W will be equal to 0. So everything over here is going to be greater than or equal to 0, or greater than 0. This will be equal to 0, and this will be less than 0. So all these things over here are negative classified, and then all the things over here are positive classified. So let's try to visualize what happened there with that update. So this first example, the vector is actually just a 0 vector, and so it actually maps everything to this point, right? So it's going to make everything negative. But let's just imagine that the vector was here for a simpler time to visualize it. So what would happen is that we would got negative 2 to 2. So that would have been, okay. So let's make it misclassify. So let's say that, let's say the vector was pointing this way. negative 2, 2. So this guy, he thinks that it should be negative, right? But actually the class is positive, so this is misclassified. Now watch what happens when I update the weights. What updating the weights does is effectively rotate this W vector until it's pointing in the same direction as that point. And now you'll see, right, that the decision boundary does a complete 180 degrees, and this is correctly classified now. So if you make the vector align to where the point is exactly, then this will make it the strongest possible way for it to classify that direction, right? So if this thing was negatively classified, then I would shift in the exact opposite direction. So for example, if, let's say this was a negative point, right? So then I will want my vector to be pointing this way, because this is going to be the strongest possible way to make it negative. And so when I just do this iteratively at each step, then what that eventually converges to is some vector that correctly classifies everything. Okay, and then yeah, you can keep doing the updates, so let's do one more. What should the next one be? So negative 2 times negative 2 is 4. 2 times negative 3 is 6. It's negative 6, so negative 6 plus 4 is negative 2. Okay, correct, good. So negative 2 is the same sign as negative 1. We're good, let's move on. Negative 2 times 2 is negative 4, plus 2, so that's negative 2. And that is incorrectly classified, so it's plus 1. So what should the new one be? What should our new W vector be after this?
It would be 2, 4.
So we think it should be 2, 4. Can you explain what the reasoning is there?
So y,
Yeah.
yi is positive 1,
Mm-hmm.
and xi is so xi is 2, 1. So then no, it's not 2, 4. It's 0 and 3.
Great job, yeah, that's correct. That's correct. So I'm just going to add these two, right? Yeah. All right, good stuff. And then we could do this again, right? So 0 times 1 is 0. Negative 4 times 3 is negative 12. Great, that's correct. And what you want to do is you want to iterate through the entire data set once to make sure that this guy actually works for everything. So let's do that. 0 times negative 2 is 0, plus 2 times 3 is 6. That's correct. Okay, 0 times 0, or 0 times negative 9 is negative 9. That's correct. And then 0 times 2 plus 3 times 1, that's 3. All right. And that's awesome, great. We got something that works for the entire data set. And what's really interesting, you'll notice, is that this is 0, right? That means that we're disregarding all that information. And look, this is always the same sign as that, right? So we could have just had 0, 1, and this would have classified everything correctly. Okay. All right, problem 8. Why might there be overfitting in decision tree, and how do we print it? All right, the answer to the second question was printing. But okay, so why might there be overfitting in a decision tree?
Well, if you don't implement any like purity threshold or like max height of the tree, it might, if there's a lot of different features, it might make like a really complicated, really high tree.
Yeah.
When in reality, like the actual information gain at some of those lower levels is probably next to nothing.
Yeah.
And you just have a bunch of excessive computations for what essentially could have been produced much more efficiently.
That's great, that's exactly right. Okay, next question. All right, so concept learning. So we're going to be talking about the sizes of hypothesis spaces. Let's say that we have 5 binary features, or 5 binary attributes. What is the size of the hypothesis space?
Isn't it 2 to the power of the instance space?
Yes, that's right. And what is instance space?
If they're 5 binary, it would be 2 times 2 times, so 2 to the 5th.
That's exactly right. Which is 2 to the 32. Okay, next question. What is the space of the conjunctive hypothesis space without internal disjunctions? So CHS without internal disjunctions. Anyone tell me that?
Basically 3 to the 5th.
And how did you get that?
Just 2 plus 1 for each one.
Exactly. What is it with internal disjunctions? Yeah, I don't know either. No, it's 3 to the 5. And the reason that we get that one is 2 squared minus 1 to the 5. Where do we get this one? I actually don't know. So we made this midterm, so this question is not one I'm too familiar with. And then the last one is, if we're giving integer values to each of them, then how many possible classifiers are there? So if we have integer values for each of our attributes, how many classifiers do we have?
Can you repeat that?
Yeah, so for each of these attributes, like let's say sunny or cold, or sunny or like rainy, right? If we make this one 0 and this one 1, and I make that true for all of them, then how large is the hypothesis space? Like how many hypotheses can I have? So the answer is actually there should be infinite. Because now instead of hypotheses, I have weights, right? And my weights belong to the real space. So there's a continuous amount of weights, therefore infinite classifiers, infinite weights, yeah. So that's it, guys. Yeah. Thank you so much for your
I
time.
think I know the 2 to the 2 minus 1.
Oh,
That's the number of subsets of 2 elements.
can you explain again?
So if you have like n elements in one set, and then the number of subset of that set is 2 to the n minus 1.
If you subtract the null set, yeah.
Yeah, subtract the whole set.
So why are we raising to 2 here?
So 2 to the 2, because there are 2. It's binary choice, right?
Right. Okay, I think I see what you're saying. Yeah. So before here it's 2 plus 1 because we have A, not A, or A and not A, right? And then here we have like all the possible combinations except for nothing. So that's also 3, which is A, not A, or A or not A. So it turns out to be the same in this case. But if you increase like to 3 or something, then it would be different because I could have like 2 to the 3 minus 1 total number for each one. Oh yeah, that makes sense. Yeah. Thank you. All right, that's it, guys. Thank you.